When we assign the exact same multi-step task to a small model, the mechanics change. It begins accurately, but immediately loses track of the original context across successive steps. This is reasoning drift. The model abandons logical constraints mid-generation to chase a plausible-sounding tangent. At this stage, the model has stopped answering your prompt and is only generating text to align with its new trajectory. Once this drift begins, it is virtually impossible to stop. The model's context window becomes poisoned by the outputs of its own previous steps. Severe hallucinations emerge as compounding, cascading collapses of logical tracking across multiple steps. To counter this drift, developers turn to external constraints, clear instructions, system prompts, and strict operational boundaries. This boundary box represents the assumption that placing strict limits around a local model will contain its output and enforce accuracy. Architecturally, a large model is equipped to follow these paths, but small models lack the continuous attention capacity required to hold external constraints in memory over a long generation. Despite explicit instructions, the small model ignores the defined path. This constraint failure is driven by a specific missing component: uncertainty calibration. Large models have the capacity to evaluate their own knowledge gaps and recognize when they are hitting a defined boundary. When they reach that limit, they are highly likely to halt generation safely, returning statements like, "I am not sure," or "this may be incorrect." Small models fall into a confidence trap. They do not know when they lack information. Without an internal uncertainty meter to trigger a halt, they default to answering every query with absolute blind confidence. This makes small model hallucinations particularly dangerous for enterprise applications, where a fully fabricated answer arrives formatted to look highly authoritative. You cannot command an AI to respect a boundary it lacks the capacity to remember. Looking at these inference pathways side by side, the mechanics of hallucination become clear. A model fabricates information whenever it must choose a path forward, but lacks the internal signal to choose correctly. Due to heavy parameter compression, small models operate in a continuous state of low signal. This is the signal-to-path deficit. Operating in a constant deficit strips away the model's structural control over the sequences it ultimately selects. Hallucinations represent deterministic outcomes of an architecture locking into place. Small models hallucinate because their Heimlich-compressed architectures provide them fewer valid logical paths. This structural reality dictates the fabricated paths they are forced to choose, regardless of the prompt used. Ultimately, small models simply possess vastly weaker structural control over the sequences they generate.